Okay, good morning everyone. So the announcements about exam 2 are right here. The only additional thing is what are the mechanisms included in the exam that I didn't include in yesterday's lecture. So there are 3 mechanisms that are included, and here is the chapters in which you can find these mechanisms. So today we're gonna keep going with the chapter 21, which is lecture 13. So we ended the lecture yesterday discussing the reactions of acidic chlorides and the general reaction of the nucleophilic addition in an acidic chloride or acid derivative. So we're gonna keep going with some more reactions. So the ones that we discussed yesterday, we had a nucleophile replacing the leaving group in the acid derivative, and in specific the acidic chloride. Now I'd like you, for each one of these slides that we're gonna go over, I'd like you to look at the starting material and the end material and ask yourself, what is it changing? Is it a nucleophilic addition? Is it another type of reaction? So let's start with this one. So this is an acidic chloride, and in here we're ending up with a tertiary alcohol. This R in here is this R, and this carbon that has the OH now used to have the C double bond O. And looking at it, we have 2 same R prime group. Does that remind you of any reaction we discussed before? So going to tertiary alcohol, 2 same R prime group. First of all, is there a change in the number of carbon from how is it represented right here? And clearly yes, because we're adding 2 R primes. These R primes are carbons. In here they are represented as R prime, but these are addition to that carbon of the carbonyl. So this reaction is Grignard reaction with acidic chloride, the same as the Ester reaction with Grignard. So in here, if we add 2 equivalents of RMgX followed by H3O plus at 0 Celsius, what we're gonna end up with is the 2 R prime groups attacking the carbon of the carbonyl, changing it to that tertiary alcohol. It's exactly the same reaction we learned for the ester in chapter 19. And that would be R prime, R prime. So, in other words, if we're going from one acid derivative to the other, it's a nucleophile that we're adding. But in here, we're changing the acidic chloride into a tertiary alcohol, 2 different R prime group. In other words, Grignard almost react with everything. It reacted with ketones, with aldehydes, with esters, with acidic chlorides. For esters and acidic chlorides, because they are acid derivative, it's the same trend. It's going to be tertiary alcohol with 2 same R prime group. The only functional group that the Grignard was quenched with is the carboxylic acid. Okay. So let's look at this reaction in here. We're starting with an acidic chloride. We're ending up with a primary alcohol, and if I map it, this R is this one, this carbon is this. Is there a change in the number of carbons in here? No change in the number of carbons. Is it an oxidation or reduction? Since it isn't a change in the number, is it a nucleophilic attack that the Cl is replaced by a nucleophile? Is the Cl replaced by a nucleophile in here, then the carbon of the carbonyl still there? No. Is it a change in the number of carbon that it is a Grignard reaction? No. It's simply the reduction, a reduction reaction in which I'm reducing the C double bond O into a primary alcohol, and the reducing agent that's gonna reduce that is the same reducing agent that reduces ketones, aldehydes, ester, carboxylic acid. Add to that acidic chloride, which is lithium aluminum hydride followed by H3O plus. Sodium borohydride would not be able to do this reaction. So lithium aluminum hydride will do it. It's exactly the same with the esters, with the carboxylic acid. So Now the last reaction of the acid chloride is this one in here. So we've seen organocopper lithium before one time in chapter 19 with an alpha beta unsaturated ketone. So with an acid chloride, if I add organocopper lithium, I'm gonna call this R prime so that you can see the difference. We're gonna end up with a ketone. So we can start with an acid chloride, end up with a ketone. So what I'm gonna do next is I'm gonna summarize all the reactions we learned about about acid chloride so that you can see the big picture. So here we go. So I'm gonna first start right here with an acid chloride. I'm gonna say how to prepare this acid chloride. So we learned that to prepare acid chloride, we start with a carboxylic acid, SOCl2, 80 Celsius. This is the only method we learned in this course, how to prepare that acid chloride. Now, anything below the acid chloride is the reactions of acid chlorides. So first, I'm gonna talk about from acid chloride going to ester and to amide, since these are lower in reactivity than the acid chloride. So if I want to go from the acid chloride to the ester, I'm going to use ROH and pyridine. The pyridine is to neutralize the HCl that's going to form. So I'm going from the acid chloride to another acid derivative. I can also prepare amide from the acid chloride. And I can use two equivalents in this case of NH3 or NH3, the amine, and pyridine in the presence of pyridine. The first mole of the NH3 is to attack as a nucleophile. The second NH3 is to neutralize the HCl that's going to form. Another reaction that an acid chloride can undergo is being reduced using the most famous reducing agent. So it's going to be reduced to primary alcohol. Also the same as esters, acid chlorides react with two equivalents of Grignard. To end up with a tertiary alcohol, same two R prime groups from the Grignard. The very last reaction is what we just talked about a minute ago, is the prep of ketone by using organocopper lithium minus 78 Celsius. So as you can see, there is a trend that you can remember this reaction. If I'm preparing other acid derivatives, it's the nucleophile. Because we're starting with acid chloride, we're always going to need the pyridine. Reduction, which is a primary alcohol, the same as any other acid derivative that we're going to see. It can also react with Grignard in the same trend as an ester. Now, going to the ester, the prep of ester and the reaction of esters, we're going to repeat some of the reactions because the prep of ester is the reaction of acid chloride. So mostly in the upcoming two slides, we're just going to repeat exactly the same reaction, but in the context of that one. So the way that I put it together is I put already the reaction concept map for ester prep. And what I want you to do is to stop the video and try to fill this reaction map. And it's all about how to prepare the ester. For those who are in class, I'm gonna open the iClicker just to track you to see when you're ready to hear all the prep. The prep can be from this chapter or from the chapters before, so we're putting all together on the same slide. Okay, so I'm gonna start with the prep of ester from acid chloride. So we're going from one acid derivative to the other. Clearly the Cl is replaced by R prime O, so it is R prime OH, but since I'm starting with the acid chloride, I need pyridine. Now, we also learned in chapter 20 that we can prepare esters from carboxylic acid. This part of the ester is coming from the carboxylic acid, and the one circling in green is coming from the alcohol. So ROH, H plus, and heat. So this is another method to prepare it from carboxylic acids and alcohols. The third method is looking at the ester saying, okay, it's coming from the carboxylate. So in other words, let me remove the tags. So we're looking at it, this is the part that is coming from the conjugate base of the acid, and this is the alkyl halide. So this one in here gonna attack the Rx, where X is bromine, chlorine, iodine. And these are the three methods to prepare esters. From acid chloride, from carboxylic acid, or from its conjugate base, the conjugate base of an acid with an alkyl halide. Okay, the next is we're gonna go over the reactions of esters. Any question about any of these? So, almost all the reactions in this slide we went over except one, but you can deduce it. So also I'd like you to stop the video and try to kind of figure out the reagents. So what I'm trying to do is to put all the reactions, then in 2 minutes we're gonna start applying the reactions, all the reactions. So we're gonna do a lot of iClickers and practice a lot, but after kind of we put each reaction in its context. So please stop the video, fill this reaction map. Okay, so I'm gonna start from the ester to this. Always ask the question, where are we going from to? We're going from an ester to amide. So we're going from something of an acid derivative with a higher reactivity to a lower one. So that is the reaction gonna take place. We learned that going from one acid derivative to the other, it's just a nucleophilic attack. So I just have to figure out which part was replaced. Clearly this OR prime is replaced by NH2. So my nucleophile will be NH3 in here. And here we're not gonna add pyridine because we don't have acid chloride. We're not forming Cl minus, that's gonna be HCl. So we don't have that. Now looking at this, this is an ester. We're ending up with a tertiary alcohol, two same R prime group. What is this reaction? And clearly two R prime groups, that means more carbons added. What is that? Grignard reaction. So that if I add two equivalents of the R prime MgX followed by H3O plus at 0, I'm gonna end up with the tertiary alcohol. Almost the same scenario as the acid chloride with the Grignard. Now this in here, I'm gonna skip this one and just come back to it. So in here we have this ester. We ended up with a primary alcohol. Go ahead. Very good. It's a reduction reaction, lithium aluminum hydride followed by H3O plus. Now the very last reaction is this one in here, where I'm starting with an ester ending up with a carboxylic acid and alcohol. In the slide before, we just did a revision that I can prepare the ester from carboxylic acid and alcohol, right? that reaction is an equilibrium reaction that goes back and forth. So this in here is an equilibrium which goes back and forth, and it's called Fischer esterification. So this in here is the reverse of that reaction. I can prepare ester from carboxylic acid and alcohol, but also the reaction is equilibrium and it can go back and forth to the carboxylic acid and R prime OH if I add a heat, IH3O plus heat, an acid and a heat. Almost the same condition of the forward reaction. Do you have a question for me? Fischer esterification. So these are all the reactions of esters. Since the amide is the least reactive, mainly we cannot prepare any other acid derivative from it. We can prepare any other acid derivative from it, but it can be prepared from all the other acid derivatives. So again, all the reactions that we learned, they are the prep of the amide. So just bear with me, I'm gonna repeat those reactions just in the context of a prep of amide. So if I'm starting with an acid chloride going to the amide, I need two equivalents of NH3. The first NH3 to attack the carbon of the acid chloride, the second one is to neutralize the HCl. I can prepare it from ester by adding NH3. I can prepare it from anhydride also by adding the NH3. Now the requirement in here that the amine should be primary and secondary, not tertiary. The tertiary amine is slightly bulky and it causes steric hindrance for the attack to take place. So it's for primary and secondary amine, not the tertiary one. So these are the preps of amide. Now with that said, some amides can have NHR. So the difference is that the nucleophile in that case is NH2R or NR2, then the amine is NHR2. And the reactions amide is kind of the least reactive of all the acid derivatives. So it's the same as the ester can go back to the carboxylic acid, the same as the acid chloride can go back to the carboxylic acid by adding water. In here we can do hydrolysis, but we need heat and we need either H plus or OH minus. Just a quick reminder, or just to connect the dots, where in our in a biological system there is amide as a functional group? Go ahead. Amino acids, and the amide itself is in protein. When proteins are formed, there is an amide bond. Now, clearly this amide bond, because amides are not that reactive, and that's a positive thing that they aren't that reactive, that we need H3O plus and heat for the hydrolysis to take place. So that's good that just we don't have our proteins just with water alone, it can hydrolyze. That can be a big problem, right? So for an amide, because it's the least reactive, when I put it in H3O plus, it goes back to the carboxylic acid plus NH4 plus. So this one will leave as NH4 plus because we are in an acidic condition. The idea is we're ending up back to the carboxylic acid. The reaction is not that different in an OH minus heat. It's gonna go first to the carboxylic acid, but since we are in a basic condition, that acid will go to its conjugate base, and the ammonium, it's gonna be an H3. So this is the hydrolysis of an amide. And since it isn't that reactive, it undergoes only hydrolysis and reduction. Guess what is the reducing agent that we're gonna use? Exactly, the lithium aluminum hydride, H2O. Exactly the same one that we've been using for all of them. Now, I want the attention of everyone in the class, because this is a very common misconception. I've seen it in every exam. I put a reduction of amide and I see the same mistake. So in the reduction of ketones, aldehydes, esters, carboxylic acid, always we ended up with an alcohol. In here, it is an exception. When I add lithium aluminum hydride H2O, I'm gonna end up with RCH2 and H2. So this will end me up with an amine. This whole thing is reduced in here, the whole C double bond O, and it has to do with the mechanism. So I know that the trend been always a primary alcohol for all of them, or for the ketone secondary alcohol. Please pay attention that this kind of drift out of the trend in here. So keep that in mind when you're reducing amide, you're going back to the CH2, not COH and H2. With this, that's all the reaction. And this, as you're gonna figure out that after chapter 19, things get much easier in the sense there isn't that much of limitations and things to consider. So what we're gonna do is kind of some questions, multiple choice questions, and couple of multi-steps, and we'll be done for chapter 21. So let's start with the first question. In all of these slides, the question is, what is the major product? I highly recommend that you have the maps next to you, all the maps that we created today, to have it next to you as we're going through this. So let's get started. Stop the video. And the most popular answer is C. C is the right answer. Very good. Again, in here we have a couple of functional groups in the same molecule, and we have to kind of figure out which one will react, which one will not. A double bond. Double bonds are C double bond. C will not be affected neither by sodium borohydride or lithium aluminum hydride. The reduction can take place with H2 platinum, H2 palladium, H2 catalytic, which is not the case in here. This is a ketone. We know that ketones can be reduced to secondary alcohols using lithium aluminum hydride. This is an ester, which is one of the acid derivatives. With lithium aluminum hydride, it will be reduced to a primary alcohol. So we're gonna choose the answer that this is the ester primary alcohol, secondary alcohol for the ketone, and the double bond is not affected, which makes C the right answer. Go ahead.
So when it's not specified, are we assuming that there's enough lithium?
That's right. So the question is, if it isn't specified, are we assuming there is enough? Yes. Unless it says one equivalence or two equivalents or three equivalents, that's another story. Okay, let's do more. Again, the question is, what is the major product? Please stop the video. C is not the right answer. The right answer is B. So the first thing when we look at, as usual, when we have a reaction, is to ask what we are starting with, especially with the acid derivative. There are a lot of them. What is this functional group in here? A C double bond OOR. An ester, very good. But it is a cyclic ester. And if you are a biology major, a nutrition major, you know those as lactones, because they have the common name. When they are cyclic, we call them lactones. So if you hear the terminology lactone, all what it means is it's a cyclic ester. Now, this is my hint for you. So if you get something like this, especially in this chapter, you should go back and say, okay, let's go to the generic reaction. We have we have the ester, we're adding H3O plus heat, which is mainly a hydrolysis reaction in which I'm gonna go back to the carboxylic acid. So this bond will be broken when the OH gonna attack this, plus R prime OH, and then the R prime OH will leave. So I'm gonna go back to the ester and see that hydrolysis. I'm gonna label this whenever it's cyclic, label it. Give it an A, B, C, D, E. The reason behind it, because I've seen some students when it is cyclic, is kind of just to throw them off. They know the reaction, but they kind of some carbons start evaporating from the molecule and things like that. So just be careful, especially as beginners. Let's label it. Doesn't take much time. So we learned that for the esters, this carbon oxygen bond will be broken, and this C, like the C double bond O, gonna be carboxylic acid, and the other part is gonna be the OH, which make it So this is carbon A, which has a carboxylic acid. Carbon B attachment should not be affected. The only bond that is breaking is between the A and the oxygen, B, C, D, E, and then the OH is attached to it, which make B is the right answer in here. Like I can give you different esters, whether open chain or closed chain, it's exactly the same as long as you know that the bond that's gonna break is the one between the C double bond O and the oxygen, and it's back to carboxylic acid and alcohol. Does this make sense? With that said, I can also give you this as a starting material and ask you what is the ester that can form. So the same as we discussed an intramolecular reactions in chapter 16, intramolecular reactions in here gonna take place. If I have a carboxylic acid and an alcohol in the same compound and I add the right conditions, which is in this case H3O plus heat, this in here will attack this one in here and form the ester. So it will still be exactly the same as the formation of an ester open chain. And we're gonna see some examples today. So I put some examples today to see the intramolecular. Okay, again, in here the question is what are or is the reagent that's needed to accomplish this reaction. So stop the video. B is the right answer. So again, we're starting with acid, chloride, ending up in here with the amide. So we have to figure out first, is the acid chloride higher in reactivity for this reaction to take place? Yes, it is higher in reactivity than amides. So in these types of reaction where I'm going from one acid derivative to the other, the only thing that I have to think about, what did I replace the Cl with? And clearly in here, I replaced it by NHCH32, but there is a limitation that the amine that I'm using should be primary, secondary, not tertiary. Looking at the amine we have in here, it's a secondary amine, so the reaction should be able to take place. Another factor about starting with an acid chloride, that always the Cl minus when it leaves is gonna pick an H and become, or a proton, and it becomes HCl. So I need something to neutralize that HCl. And this is why I'm adding two equivalents of this dimethylamine. The first one is gonna act as a nucleophile, attack the carbon of the carbonyl. The other one will be to neutralize the HCl that's gonna form. This is why we choose B over A. A has exactly the same amine, but it is one equivalence. And that wouldn't be helpful, because the HCl will form and make the amine and the amine ammonium, which is not a nucleophile anymore. Okay, again the same question, what is the major product? Stop the video right here. And I have A and C almost the same percentage, so let's check that. So we're starting in here with a cyclic ester. So I'm gonna call it, because it's cyclic, I'm gonna kind of number it A, B, C, D, E. So, but before I go further, I'm gonna go back to the reaction in general. If we have an ester and we add lithium, the most famous reducing agent in this course, and H3O plus, what's gonna happen is the reduction of that C double bond O into an alcohol, primary one, and this will leave. So the expectation in the answer is, if it is an open chain ester, two alcohols, right? One which is the primary and the other which is the result of the reduction, and the R prime OH, whatever is the R prime OH classification. Now in a cyclic compound, if I'm reducing a cyclic ester, I'm gonna end up with two OHs, but they are in the same compound because it is coming in a cycle. So this is exactly what I'm gonna do. I'm gonna do exactly the same thing, saying this should be reduced to a primary alcohol. That's gonna go to a primary alcohol. So it is an ester, we're taking it to a primary alcohol, and we're gonna break this bond. So I'm gonna call this A, this is B. As you can see, we shouldn't kind of start breaking the bonds between A and B, or B and C, because the reaction does not involve the carbon-carbon bonds. B, C, D, E, and OH. And that's make A the right answer. Does that make sense? If you can't see that A is the right answer, remember that this in here is E in here, so it's the molecule is rotated. Does this make sense? Okay. The reason that I'm putting a lot of cyclic in here, because they are the hardest, so I want to do the most challenging in class, then you do the easier on OWL. Okay, here is a multi-step reactions. You need to figure out the end product. After you're done from step 4, what would be the product? So I'm gonna stop the video right here for those who are in class. And I have C to be the most popular answer. C is the right answer. So we're starting with a primary alcohol. We're adding sodium dichromate, H+. So this is in here is an oxidation reaction. Primary alcohol oxidizes all the way to a carboxylic acid when we add sodium dichromate. Secondary to ketones, tertiary resistant to oxidation. In other words, this is a very good method to prepare carboxylic acid. The second step is SOCl2 80 Celsius. This is the only method we learned to prepare acid chlorides. So in other words, these two steps that you're seeing in this slide you're gonna see them often because they are the very two typical steps to get to the acid chloride from a primary alcohol. Oxidation of the primary alcohol followed by SOCl2 to end up with the acid chloride. Now, the last two steps, they come with each other. How do you know that they come with each other? Because you're doing Grignard. The usual is after it H3O+. For example, lithium aluminum hydride, it always comes with an H3O+. This is how you know that those two comes together. Two equivalents of pH. The pH in here is a phenyl, is a benzene ring. But to save some space, I wrote it as pH or phenyl. So we know that for acid chlorides and esters, when we add two equivalents of the Grignard, that two R's will attack the carbon of the carbonyl and end up with a tertiary alcohol. So this is the carbon that used to be the carbon of the carbonyl. Now the two phenyls are attached to it, which makes C the right answer. So this thing is very typical, at least the first two steps. I can give you, and you're gonna see that on OWL, the same two steps, then maybe esterification after that, or formation of Ammon, or Grignard, or I can keep going with any reaction we learned today. Questions? Hey, let's do more. So what is the major product? Stop the video right here. The answer is C. C is the right answer. So we're starting with, in here it's a molecule, but we have a lot of functional group in there. We have the acid, the benzene ring, the acid chloride, the OH, and we're adding pyridine. So this is a primary alcohol, and this is an acid chloride. So we learned that acid chlorides are so reactive, and in pyridine presence, that's a good sign that the HCl will be neutralized. And here I have an acid chloride and an alcohol in the same compound. Like we usually have the acid chloride plus R'-OH, an alcohol, and pyridine, and that would result with the R'-O replacing or substituting the Cl. No big difference in here, except the fact that both of them, the acid chloride and the alcohol, are in the same molecule. We call this intramolecular reaction. So this oxygen in here will attack the carbon of the carbonyl, that the electrons will be pushed up, then come back and kick the Cl. Again, whenever it is cyclic, it can be a little bit confusing. Name it or label it. So here is the benzene ring. Here carbon B should not be any different. This is carbon A. Now the oxygen is connected, which is F, is connected to the C double bond O. Let me put the F inside. The result of that is a 6-member ring. The reason that the reaction took place and the cycle is formed because it isn't that much of a strain in a cyclic compound, in a 6-member ring. Now, if it was a 3-member ring, if it's going to form a 3-member ring, that would have an angle strain and that's going to open. In other words, this is going to happen if it is 5, 6, 7, 8, and so on as a ring. Does this make sense? I can replace the C double bond Cl with acid chloride and replace the OH with an H2. Exactly the same thing, but we'd end up with an amide, a cyclic amide. Or any of the other reaction we discussed today. I can put carboxylic acid and OH, acid chloride and H2. Any of these would result the same reactions as we learned in an open chain. Okay, let's do this one. Answer is C, and this is what I was talking about minutes ago when I said, please, I need to have your attention about amides, that the reduction, the lithium aluminum hydride would reduce everything, esters, everything to an OH except the amide. And I can tell you from now, you're going to see this in the exam. Somehow, whether in a multi-steps or just a question by itself. Please, again, I put it in here just to bring your attention to the fact that adding lithium aluminum hydride to all the others, ester, carboxylic acid, acid chloride, it will end up with an OH, except for the amide. This whole C double bond O will be reduced to a CH2. There is no breaking of any bonds between the N and the nitrogen and the carbons or anything. It's just the C double bond O get reduced all the way to a CH2. Okay? Now we're going to start the multi-steps, which is in this chapter not that hard because they are very typical steps, very typical multi. So let's get started with the first one. So we're starting with bromo cyclohexane and we're ending up with this compound. As usual in multi-steps, ask yourself what we're starting with as a functional group, what we're ending up with. Did we add carbons? How many? That functional group that we have in hand in the end material, what are the reactions that we learned to get to that one? With that said, I'll leave you to do this and come back to the video. I'm gonna open the iClicker in class. I highly recommend that you discuss it even as a group of 4, 5, or the whole class, if you'd like just to talk. Okay, so I'm gonna get started with the starting material. It's an alkyl halide. We're clearly ending up with a tertiary amine, and definitely there is a CH2 added there in addition to the 2 methyls that are coming with the amine. So the question is, what are the methods that we learned about to prepare amine in this till now in this course? The only, for the moment, there are 2. Either having this nitrile reduction with lithium aluminum hydride, but this is very predictable where we're gonna go with this. It's gonna end up with a primary amine always, because always a C triple bond N is gonna end up with a CH2 and H2. So this is predictable and it's not nitrile. The other one, we learned also that we can reduce amides, and amides can have a nitrogen which is substituted. So we can use exactly the same reducing agent to end up with this in here. As we said in the slide before, the C double bond O will be reduced totally to CH2, not to OH. So I'm just gonna go backward and say, oh, you know what? This used to be an amide that we reduced so this C double bond O ended up being CH2. Does this make sense? Now the question is how to prepare amide. We can prepare amides because it's the lowest in reactivity. I can prepare it from acid chlorides, from esters. I can prepare it from either or. In this one, I'm gonna go to the acid chloride because it's high reactivity, but if you go back, like prepare it from esters, totally right. So I'm gonna say, okay, this used to be an acid chloride, and I prepared this amide from it. So I replaced the Cl with this in here, NHCH32. There is a limitation, the amine that I'm going to use. It should be primary or secondary. That's a secondary amine, so that should be okay. But since I'm starting with the acid chloride, I need two equivalents of the amine for the reasons that you probably know by now, because we want to neutralize one equivalence to attack the carbon of the carbonyl of the acid chloride. The second the second equivalence, or the other and dimethylamine, is to neutralize the HCl that's going to be formed. From there is the very two typical steps that we discussed before, which is to prepare acid chlorides. We have to go, or to start from the carboxylic acid, SOCl280. Now, in the slides before, we prepared carboxylic acid from a primary alcohol, right? In here, we're starting with an alkyl halide, and if I compare the alkyl halide to this one, it is 1 carbon more, and it is a carboxylic acid. So we're starting with an alkyl halide, we're ending up with a carboxylic acid with 1 carbon more. What are the reagents from chapter 20 that we learned that they can add 1 carbon more and end up with a carboxylic acid? Go ahead.
Is it the Mg and then CO2 and then?
Very good. The Grignard method, which is using phased and magnesium to change the bromocyclohexane into Grignard, then CO2, then followed by H3O plus at 0 Celsius to get to the carboxylic acid. The other method is the cyanide method followed by H3O plus heat. This is a secondary alkyl halide, so the Grignard is better than the cyanide method. If it was tertiary, no way to use the cyanide method. If it was vinyl, no way to use the cyanide method. If it was phenyl, which is not the case because this is a cyclohexane, that would be also a no. Does this make sense to you? So as you can see, there are typical steps. If I want to end up with an amide, I have to go to the acid chloride or ester. To get to the acid chloride, I need carboxylic acid. Then I have to figure out how to prepare that carboxylic acid. Does this make sense? Okay, one more multi-step. So again, the same question. We're starting with an aldehyde. We're ending up with this compound in here. Figure out the steps. And by the way, because I've been asked this question before, the number of errors, whether here, practice exam, or on OWL, does not represent the number of steps. So even if I put 3 errors, that doesn't mean 3 steps. All right, so stop the video right here. Okay, so we're starting with an aldehyde, ending up with a tertiary alcohol, and something special about it that it has 2 same R prime group. Now this part in here is this part from the starting material is in the end material. So clearly there are 2 phenyls that somehow we added to this molecule. If I add Grignard to aldehyde, I'm going to add only one of them. I can't add 2 phenyls. Now we learned that to prepare tertiary alcohol, it's going to be either a ketone or an ester or an acid chloride. These are the ones that end me up with a tertiary alcohol with a Grignard, with adding carbons in there. Now, we learned esters and acid chlorides can do that. So in this case, I'm going to go backward and say, this used to be my acid chloride. Not that it is wrong if you say an ester, and I'm going to draw that. And whatever left is the 2 equivalents of Grignard, which are the 2 phenyls, which is the benzene ring, that are added to the carbon of the carbonyl of that. To get to this, I know that acid chlorides are prepared from carboxylic acids. Now, comparing the aldehyde, it's 2 carbon. There is no change in the number of carbon, yet the aldehyde changed to a carboxylic acid. So that's an oxidation. And I can use chromium trioxide H+, or sodium dichromate H+ to get to that carboxylic acid. Again, if I start with ester in here, it would still be the same thing. It's just I'm start with carboxylic acid to form the ester. So that's how we can do this one in here. And this is mainly the last multi-steps in here. Now we're gonna connect this chapter what is the importance of all these three actions that we learned in this chapter. So let's start connecting the dots in here. So do you need more time on that slide? We good? Okay. So we learned in chapter 20, and this is chapter about carboxylic acids. But at the same time, these acids or fatty acids, at the end of the day, they are acids, and the reaction we discussed apply to those. So here is a list of some fatty acids that they are naturally occurring, and usually they are in our diet, and they come either from animal or vegetable kind of source of fat. As you can see, these fatty acids can be either saturated, and the word saturated, that means they don't have a C double bond C. They have a C double bond O because they are carboxylic acid, but they don't have a C double bond C. These are the saturated fatty acids. Also, there are some unsaturated fatty acids, and this is a reference for those that has at least one C double bond C. If you look at the number of carbons and count them, they are always an even number of carbons. The reason behind it is it's how synthesized in the biological system. It's always going to be an even number. Now, if we look at the melting point, we figure out that the melting, this is in Celsius. The room temperature usually is around between 20 to 25 Celsius. We can see that all unsaturated fatty acids are liquid at room temperature. If you look at the melting point, their melting point is below the room temperature in Celsius. So these are the oils that we use in like olive oils, like any other type of oil, corn oil. I can keep going, whether from vegetables or animals. Saturated fatty acids, they are solid at room temperature. If we look at their melting point, as you can see, all of them, they have a low melting point, but they are solid at room temperature. These are the butters that we use, the animal fats that they are solid at room temperature. With a little bit of heat, they kind of melt, and this is how we use them in cooking. Now, in addition to these fatty acids that I'm talking about in here, actually, let's go back. Which is healthier to eat or to consume, saturated or unsaturated? Saturated fatty acids. So the reason behind that is not that the unsaturated is not healthy, but in industry, when they have the unsaturated, what they do usually they hydrogenate it, and you know the reaction, which is the addition of H2 to a double bond. When they do that hydrogenation process to take it to the solid, some isomerization take place. It goes from the cis. All of these fatty acids in nature, they are cis. When we have double bonds, it's a cis. Unfortunately, when we do the hydrogenation, some of the double bonds inside it, they go to a trans fat, which you probably know that this is not a good fat for our body. The reason behind it, our biological system never encountered the trans fat before this age of all hydrogenation. So the body kind of get confused about the trans fat, and they have a different metabolism for the trans than the cis fat. And this is why saturated fatty acids are usually more healthy than using hydrogenated. They use the term hydrogenated because they don't want to say it's a trans fat. And nowadays you see on every chips, on every thing that we consume, no trans fats, referring to that they didn't use a hydrogenated one. Yes. Right. So one thing that also something that you use daily, and this is coming from a fatty acid, is soap that you use daily. So soaps usually can be prepared starting with a triglyceride, which is coming from an animal or vegetable kind of fat source. Now, in biology nutrition, it is referred to as a triglyceride. From an organic point of view, if you look at this molecule, it's a triester. It's a molecule with the 3 esters there. So we learned that esters today, we can hydrolyze them. We can get them back to the carboxylic acid and the alcohol. We can do that in here with using 3NOH aqueous, so 3 molar, 3 equivalents. For each 1 moles of these esters, we're gonna kind of add 1 OH minus to break the bond. What we're gonna end up with is a 3RCO minus and the alcohol, which is what we've seen today in our reactions. Now, usually in triglycerides, those in here are coming from different fatty acids. And it's rarely the same 3 fatty acids. These is 3 triglyceride. It could be 1 aloic acid coming from the aloic one from the other one. So it's a mixture of couple of them, not one. But in here, for simplification, I put only 1. Now, this in here is a glycerol. And you might know it by its more common name, glycerine. And it is used in cosmetic. Actually, it's a common moisturizer in everything we use as cosmetic. The reason that it is a moisturizer, it's the fact that it has 3 OHs. Remember the OH, it binds, it will do hydrogen bonding with water. So if I apply the glycerine as part of it, it's gonna start binding to the water doing hydrogen bonding. That means that it's gonna keep our skin hydrated, and this is why it is a moisturizer. So the side product of this usually is a good one. Now the question is how we're ending up with soap. This in here is soap. Because these in here are coming from fatty acids, so fatty acids are long chain carbons with a carboxylic acid in the end. So this R in here is the expectation is at least 5 carbons or more. So I'm gonna just represent that by, not good drawing. So let me redraw that. I'm gonna say, this is a representation of one of them. Hopefully it's an even number, because if it is a fatty acid, it should be an even number. Now, here is the question. This part in here, is it polar or non-polar? Non-polar. It's just alkane, and alkanes are non-polar. They have covalent bonds that it is non-polar. Usually non-polar, do they dissolve in water or do they dissolve in organic compounds? Organic. Non-polar dissolves in non-polar, likes dissolves likes. So this one, if it touches the water, it doesn't like that. And we call this the hydrophobic part of this molecule. This in here, on the other hand, is COO minus. It's ionic. It dissolves in water. It will associate with water. So we have this part being hydrophilic. Hydro means water. Philic likes, phobic hates. Hate is a strong word, don't like. Hydrophilic. So we have this molecule in here, which is the conjugate base of a fatty acid. It's kind of bipolar. It has part of it that loves the water, the other parts hates the water or don't like the water. So this is the key for a soap. All right, let me explain. If I have a soap molecules and I put them in contact with water, they self-assemble without me interfering. They start assembling in a way, let's say this is the water. They start assembling in a way that the inner part, the non-polar parts, comes next to each other in a sphere. Like the inner circle of this sphere, or the inner side, is all hydrophobic. And the outer part, all the COO minus, are toward the outside hydrophilic. And here comes the magic. Let's say we ate burger, pizza. We have a lot of fats on our hands. These fats by themselves, they are non-polar. They are oils. They are longer chain of fatty acids. So I think you all know, you've done this experiment before. If you just put your hands under the water, it's not gonna be clean, because the oil not gonna dissolve in water. Those fats not gonna dissolve with water. And here where you know that you need soap. And when you just use the soap, what's gonna happen? The oil, the grease on our hand will, okay, it's non-polar, so it decides to go to this side. So it's gonna end up in the inner side of this micelle or this sphere. And this whole COO minus, think about it as a carriage for all, because it has COO minus from the outside, it's gonna carry the whole molecule and wash it out, like wash it by the water. And this is how soap weight made by this. Now this assembly, you know, if you're a biologist, you know about it in the phospholipid layer. And the phospholipid layer exactly the same. The longer chain gonna associate with each other, and the minus a charged phosphate kind of point out. It's exactly the same idea, hydrophilic, hydrophobic association inside the bilipid layer. Does this make sense? Cool. So this is some of that one. Now what I'm gonna do next is quickly go over the naming. I don't want to spend too much time on naming of the acid derivatives. So first of all, let's talk about if I have chlorides, and this might look better. All right, so for acidic chloride, figure out the longest chain and name it as if it's coming from an acid. So this, if it is an acid, it's pentanoic acid. I'm gonna cross the ic acid, replace it by oil chloride. So pentanoic. So I'm gonna cross the oic and replace it by OYL, or the IC, the ic, and replace it by pentanoyl chloride. If it is a bromide, definitely it's a bromide. Iodide, it's iodide. So for this one, if it is an acid, it will be benzoic acid. I'm gonna cross the ic acid, replace it by OYL. Okay, so this is for the chlorides. What I'm gonna do, I'm gonna skip the naming of anhydrides, and you're not responsible for it. So I'm gonna just quickly just these, because you're rarely gonna encounter an anhydride. So we're gonna go to the esters. When we're naming the esters, we're gonna take it in two ways. This part that is, we're gonna consider this as this is the part coming from the acid. We're gonna name it as if it is an acid, but we're gonna replace the ic acid by 8, ATE. And this part that is connected to the oxygen, we're gonna name it as alkyl. So 1, 2, 3. So this is propanoic acid. I'm gonna cross the ic acid, replace it by 8, propanoate. And this, since it is connected to the oxygen, I'm gonna call it methyl propanoate. So the part that has the C double bond O, we're gonna think about it as if it is coming from the acid. Name it ic acid, oic acid, cross the ic, replace it by 8. And then whatever is the alkyl connected to the oxygen, name it as alkyl. So we can take two more examples. 1, 2, 3. So again, propanoate. We have an ethyl, so it will be ethyl propanoate. I'm just making sure we are on the same page. Okay. In here, 1, 2. So it is ethanoic acid, so ethanoate. Methyl, so it is a methyl ethanoate. Now, usually you're gonna see the ethanoate as acetate, because it's coming from the acetic acid, and the acetic acid is common name of ethanoate. So you can see it as methyl acetate. Yes?
Is that a space between the methyl and
Yes, there is a space between the ethyl and the propionate, the methyl and the ethanoate. Thank you for asking. Now, lastly, the amides. How do we usually name them? Again, take it as if it's coming from a carboxylic acid. We're gonna cross the oic acid, replace it by amide. So in here, I have, when I say CH2 bracket 4, what does that mean? There are 4 CH2s connected to each other. So in here, this translates to NH2, 1, 2, 3, 4, and the methyl. So 1, 2, 3, 4, 5, 6. So hexanoic acid, I'm gonna cross the oic acid, replace it by amide. So hexanamide, and in all of them, we don't say where is the amide because it has to be carbon number 1. Now, there will be cases where, like this one, where the nitrogen of the amide has substituents. So first of all, name it as if it is a carboxylic acid, and if it is a propanoic. So I'm gonna put it propan amide. Now, if I say dimethyl, it wouldn't be clear for the person who's reading it if the methyls are connected to the nitrogen or to this part of the molecule. So according to IUPAC, to represent or to tell whoever is reading the name that those methyls are connected to the nitrogen, we use the prefix N. So when I say, because these two methyls are connected to the nitrogen, so I'm gonna put N, comma, N, dash, dimethyl, propan amide. If it is ethyl, ethyl, propan, amide, and so on. So this is the naming. Now, I just wanna, what time is it? All right. Okay, we're gonna stop right here and we'll keep going on Monday, probably with chapter 22. Enjoy your weekend. I'll see you Monday.